First of all, I would like to bring three runtime variables to your attention, which you can control. I will show this in a second, both from the PyAlf Python interface, but also from the parameter files directly, if you don't use the PyAlf interface. And the three quantities which control observable measurements are L tau, ops start, and ops end. L tau, if it's set to 1, then the time displaced correlation functions are being calculated. Any other value will turn those measurements off. The reason is that time displaced measurements take both quite a bit of CPU time, but also quite a bit of data storage. And one is not necessarily always interested in the dynamical quantities. Especially if you calculate the phase diagram, you might want to go to a larger system size instead of knowing the excitation spectrum. And then with LOPS start and LOPS end, you can define the interval on imaginary time where you take the equal time correlation functions. So the imaginary time always goes from 1 to L trot, and then the relevant interval in which you measure is restricted to LOPS start and LOPS end. Those are typically set, or one can typically stick with the default values, which means that one will measure on the whole interval. So notice that LOPS start, LOPS end equals 0 does not mean that you measure only on the first time slice, but you will measure on all of them. Okay, so this will be the place where I show you the terminal. And I'm here in the directory where we had the Python script. I'm assuming that you're all familiar now with how you can run the Python files. What I want to show you instead is if you were to look at the Python script, let's go to edit anyways. Then there's a bunch of variables, one of them being here, L tau, and you can set it to 1 or to 0 to turn it off. I think you have seen this already in the tutorials. But then when you have run this Python script, then you can also see this in the data where the Python has, the ALF has been running, and the Python script generated a parameters file, which is then used by the fortran code of ALF. And again, you will find it's a little bit further down here in the section of the QMC variables. You will find those three. Sure, if I can highlight them. You can find those three variables I was talking about. Right. And then in addition to the PyAlf interface, of course, you also have the data file present here as well, like the raw data, which you can either look at with using this PyAlf, but you can also view the files directly. And let me highlight a few aspects of them. So first, looking at the, say, the kinetic energy, which is a scalar observable, you can here see all the data files or all the bins, the measurement values that have been produced. This first quantity in that file counts how many elements will be following in the same line. In this case, it's 2, because first you have the kinetic energy with the real and imaginary part. And then you have the sign of this configuration. Since this is the Hubbard model, there is no sign problem, it's always 1. And the analysis also produced the file where you have the expectation value of the kinetic energy and its error. And since the kinetic energy was the first variable, this will show up as ops1 providing here the information that the kinetic energy is minus 13.7 with an error of 0.017. Similarly, you have data files for the equal time correlation functions. They will also always end with underscore equal. And then the analyzed version where you always have this additional j, and it's either jk if you talk about momentum space, or it's jr for the real space resolved Green's function. The difference is that one is the Fourier transform of the other. And finally, you also have the time displaced data. For example, if I look still with the Green's function, this is not stored in a single file, but in a whole list of directories. In this case, you have the Green's function for momentum 0.45, 0. So 0.45 is the x coordinate, while the 0 is the y coordinate. Since I was using this one-dimensional example, the y coordinate doesn't make an awful lot of sense and is always 0. Right. And then I won't go too much more into detail into the file structure of those files, but you can find this on the documentation. Are there questions until this point already? Because now we will start switching gears and go further into the Fortran source code. Okay, this does not seem to be the case. Jefferson, was there a question?
No.
Okay. Now, since people asked yesterday, let me be very explicit in where this observable measurements are defined in the source files and list all the relevant routines which contribute to observable measurements. So first of all, this is all defined within your Hamiltonian files, which you can find in your ALF directory. Then there's the subdirectory proc, Hamiltonians, and you will find there a bunch of already pre-implemented models. In this case, it's the Hubbard model with the F90 for the Fortran ending. And within this file, I will show you this in a second, there are 3 subroutines which typically change, and then 2 others which usually don't change and can therefore be easily included from this Hamiltonian Hubbard file. But let's get back to this later. The main routine is the alloc ops subroutine, which defines and declares all the different observables that you want to measure. It will allocate the memory required for this. It will define the file name in which you want to store the data. Yeah, that's the main purpose of this routine. And then there are 2 kind of similar routines. The obser routine, which is taking the equal time measurements. And then there's the second version of it, obser-t, which is taking care of all the time displaced measurements if you're interested in dynamic quantities. The last 2 routines are the one where you actually print the data onto the disk so that you can have a look at it afterwards. And the init routine is initializing the memory that you have allocated in the first one, or it is resetting the results after you have stored the information on disk so that you can start simulating a new bin and start a new sequence of measurements. Let me show you one more slide before we switch to the source code. And this is about predefined observables that you can call within obser-t or obser. And again, I'm at this stage mainly listing the names of those functions And you can find the details in the source code predefined observables or also in the documentation. The main functions are predefined measurements for the single particle Green's function. And then as you can see already the pattern here, if I want to know the density correlation function, then I replace green by density or by spin SUN MC for spin-spin correlation functions. One has to distinguish spin SUN from spin MC because the SUN model is, even after Hubbard-Satonovich decomposition, explicitly SUN invariant. So it doesn't make sense to distinguish the X, the Y, and the Z component of the spin-spin correlation. While for the MC decomposition, or if you introduce an explicit magnetic field in the Z direction, this is no longer the case, and it makes sense to distinguish the Z component from X and Y. Exactly. And then fitting into the same pattern, replacing equal by obs tau will provide you a similar predefined routine for the time-displaced version of it. And allow me to do a little bit of advertisement here as well. If you find that there is a observable which is probably generic and many models would be interested in measuring something, which is still missing here in this list, please feel free to open an issue either on GitLab to tell us, hey, that would be a cool observable that we should implement. Or also you could implement the routine yourself and then share the solutions with others by the same means of Git. Okay, so enough about this names of functions and what they do. Let's jump into the source code. And here I want to look at and start with the Hubbard model where we actually use the predefined functions and then walk our way further and further. And in the end, we will get our hands dirty and look at Wick's theorem and how to implement an observable yourself. Alrighty, so we are looking at this Hamiltonian module where there's a header containing the copyright and so on and so forth. And then within this Hamiltonian module, we have declared 3 types of observables. There is this obsvec reappearing for the scalar observable, and that's also why this array is called obscal. And then we have 2 versions of this lattice class of observables, once for the equal time correlation functions and another one for the time displaced. At this stage, this is just the definition of a name, but there is not an awful lot of content behind this yet. Let me scroll down here. I won't discuss all of the routines. Ham set is what the name is doing, setting the whole Hamiltonian. Ham lattice with the predefined lattice structures was discussed yesterday by Jonas. And then if you go further down, we arrive at the first subroutine that I've listed on the slide, namely the subroutine alloc obs, which, as I've promised, is defining which kind of variables you have. So let's go through this a little bit more slowly. In this line here, we define that we want to have scalar observables. More precisely, we want to have 4 different scalar observables. The first one will be the kinetic energy. The second one is the potential energy, the particle number, and the total energy. And with this routine here, where we make the observable of type vector, we are actually creating the memory that is required to take all the measurements we want. And then in a similar fashion, we define the equal time correlation functions. Here in this example, it's 5 of them. containing the single particle Green's functions, spin-spin correlations, and density correlations. And they will be stored in the file names that we have just specified here. Exactly. And then there is the same thing for time displaced correlation functions. So if you were to add a new observable to one of your models, you would have to increase the size of your, or the number of your observables, and you have to provide the file name in which the data is stored. And for time displaced functions, we like to distinguish particle quantities from particle hold quantities, because correlation functions like the spin-spin or density-density correlation is always particle hold symmetric, and one can use the symmetry to get better results. Okay, so this was the allocation routine. And then here in this observe routine, which is doing the equal time correlation functions, we use the predefined observables so that it's very easy to access those generic correlation functions. And let me show one example, both for a scalar observable, but also then for spin correlation functions. So in the scalar observable, I chose the particle number. The particle number is, can I write here? So the particle number n is given as the sum over I, C dagger I, Ci, and sum over I. And this quantity here is stored in the GRC. We will get back to this later for the same position II element. And this is exactly what we, where is it? What we take here. And then we store it in the scalar observable. And if you want to measure the spin-spin correlation function, it is as simple as calling either the spin MC predefined observable or the spin SUN predefined observable, depending on your symmetries of the Hamiltonian implementation. And in one case, you only get the spin-spin correlation function where the components don't matter. In the other case, you provide 3 different observables because the routine will return both the XY components, the C component, and then also the total component of all 3 of them together. For more details, you can look them up in the documentation. And then, without getting into too much detail, one can repeat the same. Let me erase the annotation here first. Erase. There we go. You can do the same with observ T for the time displaced correlation function. Again, use the predefined observables and call the various types of predefined observables you are interested in. And this, as I've mentioned before on the slide part of the section, we are including this generic form of the print and initialization routines. Let me quickly show them, but you can essentially copy paste them to all of the projects you will most likely do, because it's as simple as running over all scalar observables and printing the measurements onto your hard drive for the print observables routine. And the initialization is again running over all possible scalar observables and calling this initialization function. And as long as you only change the length of these vectors of measurements, so that the number of scalar observables, you don't have to touch this part of the source code. Okay, So I'm running a little bit late, but I think we're still kind of good in time. Are there any questions at this stage? Because we will change gears once again and move from predefined structures to new observables defined by the user using Wick's theorem.
There's nothing in the chat.
Okay. Then let's move on to the plain vanilla model. The purpose of this plain vanilla Hubbard model is exactly to show a very simple and well-known example where we don't use the predefined structures. Again, like before, we define the observable scalar equivalent image time displaced. We have once more actually the same or almost the same allocation routine. And then the more interesting part is happening here. Actually, let me switch back to the slides and then move on to the source code once more. Because if I want to implement a correlation function myself, I have to reconstruct and define what is the observable that I actually want to measure. And this is readily done because if I have a fixed field configuration, I can use Wick's theorem. And this means that any generic endpoint correlation functions for equal times can be readily computed out of the single particle Green's function. And I will show you in a second. Actually, I already have it here, the definition of the equal time Green's functions that are provided in the observe routine. So what do we do if I look at a correlation function, which, for example, has this structure here? I have one pair of operators C dagger C at positions I1 and I2. This could be, for example, the density if I was at the same position, if I1 and I2 were both equal to I. But I could also have, say, nearest neighbor hopping terms here where I1 and I2 differ by one letter spacing. And then I have my second operator. So this would have been the first O at position I. And then I have this group of operators for the other operator Oj of my correlation function. Let me erase the color again. Now, so this is why a typical density-density spin-spin correlation function has this form. Now, how do I reduce this correlation function using Wick's theorem? Well, I have to contract the different options of C's with C daggers. One of them is this guy, where I contract the first with the second and then the third with the fourth. And this is generating this expression and this term here. The alternative Wick contraction is using the other pair of C dagger C operators. So taking, I wanted to change the color, it didn't work out. So let's call this here 2. So this lower section is section 2. And then I have again the C dagger C contraction at position I1 and J2, which is this term here. And then the C dagger contraction. Notice that the position of C dagger and C is different. This is this term. And while all C dagger C's are stored in GRC, the same is true for this one and this one. Only the last one, because of this exchange, can be extracted from GR. And then similarly, you can insert the imaginary time for your first two operators and use the time displaced Green's functions. One caveat you should keep in mind is this minus sign here. Yeah, but I won't go into too much more detail since I'm kind of running out of time for the time displaced ones, but let me instead show you again the source code for the density-density correlation function. we had this GRC in product with another GRC. This was the first term of weak contractions. And in this case, we are explicitly summing over the spin index, spin up and spin down. And then there was the second alternative to contract those C dagger and C operators, which generated a GRC times GR, where here we have used the spin symmetry that I can only contract C dagger and C operators if they have the same spin. That's why this summation over spin that we had on the slide decomposes into the product of Green's function with the same spin, and then I sum only over one spin. And we play the same trick. We store this result that we have just computed in the lattice element of the equal time correlation functions. And since we are looking at the density and I have to subtract the background, I subtract the background in this line here, where again, I calculate the density just like we have seen before for 0, which was in this line here. And I think with this, I walk you through the relative sections of the observables, what they mean, why the structure is the way that it is, and how to decompose generic endpoint correlation functions using Wick's theorem. Of course, if you go to m to the fourth, you would have more C dagger and C operators, but the scheme in which you decompose them is exactly the same. So thank you for your attention, and please ask me any questions.
Yes, thank you very much. So I had a question on this slide specifically. Can you hear me?
Yes, I can hear you.
I was wondering what was the difference between the brackets in 127 and 130. Why is there a double bracket in 130 and a single bracket in 127?
Yes, so it should be the same. It should always be the double bracket. Okay. I copy-pasted this from the documentation, so I think we should revisit the documentation and make sure that it's consistent. The reason why there are double brackets is that the Wick's theorem applies only for a fixed field configuration. So this is not the overall expectation value of the Green's function, but it's not averaged. So this expression here with the double bracket is not averaged over the field configurations, but it is for a fixed field configuration. So maybe I can change the pen color to black and a little bit smaller so that I can write the formula. Pen width thin. So okay, it's still red. Anyways,
you have to press OK on the window.
Yeah, I think it's happened twice by now. Ij with a single bracket is to be considered as the summation over my auxiliary fields phi of the expectation, well, not expectation value, but the contribution as Farker has defined in the lecture, Ci, Cj, for this fixed field configuration phi. And Wick's theorem only applies for the fixed field configuration. So in any case, you should have had these double brackets.
Okay, great. Thank you very much.
You're welcome. Are there further questions?
Hi. So for example, oh, sorry, go ahead.
Okay, so I was just wondering, if I make a new lattice, do I have to change anything in the measurement part? I mean,
yeah, so as long as you stay with the predefined lattices, then you don't have to change anything in the measurement part.
Yeah.
Because let me show this again. oh, no, it's not here. It's there. One argument, I was skipping over all the list of arguments in the measurement, but one argument which you provide to this predefined observable routine is both the lattice and the orbital positions within the unit cell. So if this is if you have those two quantities available, then the observable predefined structure can incorporate for the lattice that you have.
But if I make a new lattice, then I have to make some change here, right?
If you change the lattice, maybe actually let's go here. So this is the plain vanilla version, and there should be the lattice information, right? So here we are not using an explicitly predefined lattice. We could, but we don't. And the main point is that you provide, on one hand, this let unit, which is encoding the position of the orbital degrees of freedom. And you have to also provide this lattice itself, which is constructed out of the Bravais unit vectors. And then these parts of the correlation function do work as they are. There is one caveat, though. And let me show this also. I hope that no, it's not in here. So here we use the predefined observables. And this is related to the kinetic energy. Because the list of nearest neighbor bonds, this also does depend on your lattice. And if you change the lattice, say from honeycomb to Kagome, there are different nearest neighbor bonds. So then this routine will not work, because the hopping matrix, which is also encoding the lattice, is not defined for your Kagome lattice. So some will work, others will have to be modified.
Okay, thank you.
You're welcome.
Can I comment on this question?
Sure.
Johannes, the idea of the program here is that if you change the hopping matrix and you do it correctly with the strategy we have in the predefined hopping, then you don't have to change this. You don't have to change anything in the predefined hopping compute kinetic energy, for example. That should go through.
Yeah, thank you for the comment. That's perfectly correct. What I was saying, or what I was trying to say at least, is if you define a new lattice and the only modification that you do in the lattice is concerning the lattice itself, and sorry, it's not the right section of the code. Here we go. If you only change lattice and let unit, you are not yet done. You would also have to change the hopping matrix structure according to this lattice.
Yeah, correct. Sorry. Yes.
Okay, I understand now.
No further questions?
Yeah, I wanted to know if it's possible to assign a chemical potential for each spin flavor. For example, let's say we have an SU2 Fermi Howard, but I want to, well, no longer SU2, but I want to make a spin imbalance mixture. Is that possible within the?
Yes, that is possible. I think Flo will talk about this. Okay, this is again the plain vanilla. In the plain vanilla, it would be very easy because you explicitly see the chemical potential, which is written on, the Hamiltonian on the same side, and you could add a spin dependent chemical potential. But also for the predefined structures where you have, I believe it's in the ham hop, there is the option of changing, right here you pass on the chemical potential as a vector, and it is a vector precisely to have different chemical potentials for different flavors. So again, you could encode this also on this level, but I believe the way how Hubbard model, for example, is implemented right now, it only can read in one value of chemical potential. And I don't think that we allow for an explicit magnetic field, because the magnetic field would be this Zeeman coupled staggered chemical potential dependent on spin.
Yeah. Okay.
And I believe that Florian will discuss the hopping module later today even.
Today's interactions, but hoppings are
Okay, sorry, then it's tomorrow morning.
If there are no further questions, we do have a bit of time. I mean, it's a break, but we want to have as much interaction as possible, as we have said already before. So we are definitely open for questions. If not, then we're going to have now a short break in about 15 minutes. We will start again with the talk by Faka, by Professor Assad, again from Monte Carlo, and he's going to touch on the project proposals as well. Okay, so see you. Yeah, we'll be back with you soon. And thanks, Johannes, for your presentation.
Thank you.